So today we're going to talk about SHM and the graphs. So in the previous video, we talked about how we got the definition, and we talked about two conditions, which was the force always acts opposite if the force is this side. The displacement that we see is actually the other side. So the force and the displacement was opposite. Force and the displacement was in the opposite direction. And we know that force equals to mass into acceleration. So force is proportional to acceleration. So we can also say acceleration is opposite to the displacement, because if you provide force, then you will get acceleration, and when the force is zero, and so is the acceleration. So the force depends on the acceleration depends on the force. So this was the first condition, and the second one was that if you increase the force, so for instance, if you increase the force on the pendulum, it would travel a farther, at a greater displacement. So we say that force was proportional to displacement. We know that force is so as a result, acceleration is also proportional to the displacement, but as they're in opposite direction, there must be an x. So this is what we did in the previous class, and today we will see how graphs can be derived from from the oscillations of simple harmonic motion. So very firstly is the let's talk about the acceleration and displacement graph. So we see they are proportional. Like if acceleration increase, the displacement will increase. But so the graphs had to be something like this: that the acceleration increasing. If this is acceleration, this is displacement. So if the acceleration is increasing, so shall the displacement. But as this has a minus, so the graph will be similar, but it will be in the other side. So as the acceleration increase, the displacement will increase, but at the negative side. So the curve will be something like this. And let's go on to the important ones. So for the syllabus, what you need to know more is the sinusoidal curves. So firstly, let's look at a pendulum. So it's traveling from here and back to the equilibrium, and then to the right. So let's say this displacement, let's consider the displacement at left to be positive and right to be negative. So at left in the center, and at right. So so if you focus on displacement, what we see here is that at center we start from 0, right? And as we go towards the left, it's maximum here, and as we go towards the right, it's minimum. It's also maximum. Sorry, it's maximum. So from the equilibrium position, at both sides we go, it's maximum. But we can, if we consider the direction, we can write it's maximum at the positive side, and this is maximum at the negative side. As I said earlier, let's consider this side to be positive and that side to be negative. So so if I could draw a graph, like how could you prove that this this motion produces a sinusoidal curve? So we're going to see here, so So let me draw the axis. So we will focus on these points. So let me just align it with the graph. So what we see is that at left we have a maximum displacement. So from the positive axis, y-axis, we start, and as it approaches towards the center, what we see is the displacement is 0, so it must travel here. And again, as it approaches towards right, we get another maximum. So the curve is like this, and the curve follows something like this. So we get a sinusoidal curve, and so we see we can see like how a sinusoidal curve is being derived from the displacement of oscillation. And and the other thing you need to know is the equation that we get from here. We don't actually need the derivation in A2 level. Our syllabus doesn't require the derivation. So what you can see is the displacement is actually the maximum one. So this is the amplitude, or you can also say x naught. So let's say it's the amplitude, it's the maximum displacement. And another thing you have to notice is that this sinusoidal curve actually starts from the maximum. So we also know something, that a sinusoidal curve that starts from the maximum is a cos graph. So this will be cos 2 pi f, and this is the time axis, so this is t. So instead of a, what you can write is the x naught, which is also the amplitude, or which is the maximum displacement, to cos, and 2 pi f is actually omega t. So hence we derive this equation for displacement, x equals to x naught cos omega t. But if you want to really know how the derivation arrives, I will make a separate video for that. So let's proceed. So we looked at displacement graph. Now let's have a look. let's focus on the velocity. So the same, we have a pendulum which can rest in the equilibrium, which is the equilibrium point, and it can move towards the left and towards the right. So what we see is that as it approaches towards the maximum point, like it moves at full swing, and as it moves to the maximum displacement, momentarily the velocity comes out to be 0. The velocity. So let's focus on the points on the position left, center, and right. Also for the velocity time, we're going to look at left and at the center and at right. So we're going to follow the position on the graph also. So as I said earlier, so the velocity at the left, momentarily, like as you go on full swing, and over here momentarily, when we come back, the velocity over at the highest point becomes 0. So it's 0, and in the center it's maximum. But when it's traveling, if you consider this side to be the left side to be positive and that side to be negative, so if it's traveling from this point to this point, so the velocity will be maximum, but this could be positive if it travels from this side to that side. So, if this side is the right side is negative, so it should be minus. For this curve, it should be minus. But if it was traveling from right to left, so it would be plus. So it depends. And for the the right side again, we get a velocity of 0. So what we know is the curve should start from 0. So from the x-axis. So for this curve, as it's traveling from let's say it's traveling from this side to this side, so the displacement is minus. So this could also go like this, and the main thing is we have to start from the center. From 0. But for this, we are starting from the 0, and we go to so we get a maximum velocity, but at the negative y-axis. It's maximum velocity, but at the negative y-axis. And again at the right, we see the velocity becomes 0 again. So the curve will go again back to 0, and it will follow like if it was allowed to follow so the curve would follow a sinusoidal curve. So what we see here is that so the equation that you really need to know, but you don't need the derivation, is that V equals to, as we said earlier, that this could be plus minus, it depends. So plus minus 2 pi f into root over the amplitude square, this amplitude, minus the displacement square. So the syllabus doesn't require the derivation, but if you want, I will show, I will make another video for the derivations only. And the other thing is that as this follows a sine graph, this could be like the same as before, that x equals to x naught cos theta. So as that follows a sine curve, that could be v equals to v naught sine omega t. So moving on. So the last one, let's have a look at the acceleration. So similarly, the 3 positions, the left, the equilibrium, and the right. Center and the right, and here the direction, let's say this is the left side is positive and the right side is negative. So in the center we have a 0 acceleration, and at the left and the right we have the highest acceleration. So why is that? You might have a question, why? So let's have a look at 3 stages. So for understanding the acceleration at the 3 positions, we have to also know the forces acting. So we will look at an example, but we'll have to focus on the horizontal component. So let's start from the equilibrium. So what happens in the equilibrium is, so we consider that we provide no external force. We just leave it from a height, and it moves because of the weight. the only thing that works is the weight. So the first thing first, so at equilibrium we said it's 0 because, and the only so the acceleration will be caused by a horizontal force. So keep this in mind. And there is no external force given. W is the only force. So when W force is applied, or the weight is there, the reaction force, the tension over here, is upwards. So we see there is no horizontal force or the horizontal component which can make it move. It might have velocity, which is because it was left from here, but acceleration has no relation. So the acceleration here is 0. The acceleration is related with force. If there is a resultant force, you get acceleration. So as there is no force, there is no acceleration here, though there might be a velocity. So no horizontal component is contributing to this oscillation. As there is no horizontal component this side or that side, there is no force, there is no acceleration at the equilibrium position. Now let's have a look at the maximum point. So at the maximum, this is the horizontal component, and so this is the pendulum. You took it at the maximum place. At the maximum point. So it is of a maximum displacement. So this is W, and this is the horizontal component. So what you did was, is that we decreased the angle between them, the theta. So decreasing the theta increases the force on the horizontal component. So at maximum point, the reaction for weight is at an angle, right? The reaction is at an angle. Hence, we do get a horizontal component, but as the angle is shorter, the angle is less, the least at the maximum point. So the force, the horizontal component, is also the max at this point. As we proceed, as we descend, the theta increases and the horizontal component also decreases as the reaction component. As the theta increases, we know as the theta is more, if you plug into the equation, the component will decrease the other component. So hence we get a horizontal component which contributes to the acceleration, the maximum acceleration, and hence there is the maximum horizontal force at the maximum displacement. So I talked about more about force is proportional to acceleration. So increasing the force increases the acceleration. So if you just look at focus on the forces, we will get to know about the acceleration. So as it descends, the angle theta increases. So the horizontal component decreases. And so the force and the acceleration decreases as it appears near to the equilibrium. So that is what I was saying. So at center, it's 0. At left, it's maximum, the acceleration. And at right, the acceleration is again maximum. So if we draw a curve, so it's traveling from left to right. So it's minus, and the direction is it is a minus direction. So so at left it's max. So as I said, it's traveling from to a negative direction. So it will start from negative. So it's at max, but it's at negative. and at center we get 0. So slowly to this, and again at right it's maximum, but the direction is opposite. So it will be the maximum point but at the positive y-axis, and the curve will follow a sinusoidal path, like this. So we can derive an equation that the acceleration is the maximum is the amplitude, same as before, and like it goes like before, as we see, you put sine or cos according to the graph you see, the amplitude and the time. But what our syllabus requires us to know a separate equation, that is that you already know this, that A equals to omega square x, minus omega square x. So you can also write this as 2 pi f square omega, x. And from the curve we get A naught sine omega t. But this is what you need to use more frequently. So we see, but one thing you may notice is that so we saw it earlier as a condition for SHM, that is that the acceleration and the displacement is proportional, but they are opposite, in direction. So if you compare the graphs, what we see is the graphs look similar in the displacement. It starts from the maximum. For the same example, it starts from the maximum and it follows a sine curve. And same, for the acceleration also, it starts from a maximum point, it follows a sine curve. But the difference is that it's opposite. It starts from the minus, from the minus axis, and this starts from the positive axis. So we can see the relationship is working here, that it's opposite when it acts in direction. So for today, we'll leave it up to this, and let's have an overview for the equations that we saw and what you need to mostly use for your A2 questions. So first one was the displacement. It's the amplitude cos A cos 2 pi ft. So 2 pi f is the omega. It could be, instead of amplitude, you can write x naught, which is the maximum, and that is the amplitude in a way. So x naught cos omega t. This is for displacement, and for acceleration we saw, you mostly have to use its minus omega square x or minus 2 pi f square x, the displacement. And lastly, for the velocity, which you need to mostly use, is that v equals to plus minus 2 pi f root over amplitude square minus the displacement squared. So this is the equation. These are the equations you mostly need to use for the A2 syllabus. Though you can use the, looking at the curve, whether it's starting from the maximum or the equilibrium position, you can use the cos sine relationship equation. But mostly you need this equations for solving the questions in A2. So for today, we keep it up to this. See you next class.